Hi, welcome to Monitoring Serverless Applications. My name is Rachel White. I'm a technical evangelist at Datadog. I'm a full-stack engineer, but my specialty is Node.js and creative coding. If you have any additional questions outside of this talk, please feel free to reach out to me at oho on twitter.com. Today we're going to go over a few different items, including what is the difference between traditional and serverless applications, learning about Twitter bots, coding in generative art, serverless applications, specifically using AWS Lambda, and we'll learn how to monitor the serverless application we'll be building. So let's start off by learning what exactly is serverless. And to start, we need to understand where we're at with traditional application architecture. Traditional web applications have what we refer to as stacks. These stacks typically consist of an operating system, a server, a database, and a programming language. Linux, Apache, MySQL, and PHP is a LAMP stack. Mac OS, Apache, MySQL, and PHP is a MAMP stack. MongoDB, Express.js, Angular, and Node.js is a MEAN stack. And these are applications that have 100% uptime. You configure your own server and have full control over whatever technologies you're working with. We refer to these kinds of applications as monoliths because they're typically controlled via a single deployment. This means we can have quick minimum viable product, but it also means it's harder for us to change a piece of our application architecture, as nothing is isolated and a lot of things rely on each other. An improvement on that traditional architecture is microservices. And in a microservices environment, everything is separate and relates to a specific feature. You can mix technologies by choosing suitable programming languages and frameworks for each service. There's better scalability, as each service can be scaled independently according to its traffic, and each feature is deployed separately. With serverless, the cloud provider you choose runs your code, and you really don't have to think about configuring servers at all. You only pay for what you use, so you aren't paying the costs you would normally incur with a server running 24/7. It's also easier to adapt at scale by having technologies automatically scale with demand. We're specifically talking about AWS Lambda for our serverless functions. You can run code for virtually any type of application or backend service, all with zero administration. Just upload your code as a zip file or a container image, and Lambda automatically and precisely allocates compute execution power and runs your code based on the incoming request or event for any scale of traffic. You can set up your code to automatically trigger from 140 AWS services or call it directly from any web or mobile application. You can write Lambda functions in your favorite language, such as Node.js, Python, Go, Java, and more, and use both serverless and container tools, such as AWS SAM or Docker CLI, to build, test, and deploy your functions. So now that we know what we're working with, let's talk about how we can monitor those serverless environments. So our main problem that we're trying to solve is how are we going to debug a server that doesn't exist? How can we take traditional observability practices and adapt it to a serverless ecosystem? Modern infrastructure isn't simple at all. It's not just a server or two for our applications. There are many processes to look at. So how do you debug a server that doesn't exist in this environment? And serverless has very platform-specific constraints that you have to worry about. You need to think about it in terms of how much memory do we want to allocate, which we do in regular applications, but with serverless, we have to consider it for each request that comes through. You have to deal with cold starts, which happen when you execute an inactive function. The delay comes from your cloud provider provisioning your selected runtime container and then running your function. You have to deal with API gateways as intermediaries. So there's an API gateway or a queue, and then that calls your serverless application. And every year, Datadog has done a state of serverless or a state of containers where we dive into the data to see what kind of usage we're seeing within our customers. And we found that half of AWS users have adopted Lambda, which tells us that there's no doubt that there are use cases and business value for using serverless. Larger organizations are embracing Lambda the quickest, which is interesting because usually the stereotype is that larger companies are the last to embrace new technologies because there's too many blockers. Larger organizations are finding value in the serverless model the most. So how are we going to see that our serverless functions are working as intended? and Datadog makes it really easy. The first part is enabling the AWS integration. The AWS integration sets up some IAM rules and begins scraping your AWS account for information about what's going on within your infrastructure. And then we add the forwarder, which is going to ship all of the metrics for serverless back to Datadog. And finally, we instrument with our programming language of choice. And once you've done your initial instrumentation, the first thing you'll get out of the box is some metrics and a dashboard. The metrics in the dashboard give you a base to begin to rationalize about what is happening within your serverless application. In this case, we're looking at a dashboard, and there's a couple things that stick out. Base level, how many invocations of my serverless functions do I have? How many errors? How many cold starts? Having this around lets you see the base level for your systems and be aware when something fundamentally changes and when there may be something going on in your application that warrants some attention. In addition to that, let's look at some other items. Errors are an obvious one to check out. Slowest Lambda functions, top invoked functions, and top cold starting functions. Also, you're able to look at the most expensive functions to see what is costing the most to execute within your ecosystem. All of these are things that are going to give you a baseline to dig deeper into some items of what you'd want to optimize. In addition to setting up those dashboards out of the box, you might be interested in setting up some business level metrics. The whole reason we're writing software is to deliver business value, and as soon as you can get the software you're writing to quantify and track those business level metrics on a dashboard somewhere is critical to building a feedback loop. You really want to know, is your software delivering the value that your business expects, or did something go wrong, or have you introduced something that broke things? Adding metrics allows you to, for example, know how many shopping carts have been abandoned and how long it's taking people to check out. You can also see something that's once removed from serverless, but is potentially a big part of the experience of deploying serverless applications, which is real user monitoring. Potentially, if you deploy a serverless application, you want to know what your end users are experiencing. This is circling back to what is the business value that our software is delivering, and what are the trends for the underlying value that we're delivering to our customers. And speaking of deployments, one of the things that is super critical in seeing when changes are introduced and how they affect things overall is with the Deployments tab. And with the Deployments tab, we're able to see all of the deployments as they happen across time. They'll show up as events as well, and you'll be able to track over time if an error is potentially because of new software or if it was because of a change in user behavior, an attack, or something else. It gives you another data point for what is happening inside of your systems. Mentioning before, APM has language-level instrumentation for serverless applications. It's one of the biggest benefits you can get out of monitoring your software. APM allows you to see your software as services. Instead of focusing on it as a thing that runs somewhere, you can focus on it as a service that runs somewhere and is delivering a simple thing. With this screenshot, we're looking at a trace that came in through AWS Lambda. You can see that the darker green, which is the Lambda being called. And above that is the top-level span that is an API gateway calling that Lambda. Earlier, we talked about serverless applications only existing for a few hundred milliseconds, and it's not even called directly. It's called by something else. Distributed traces and APM give us a way to ration about that entire unit of work and all of the things that happen with it. So we can see the original API gateway call, the subcall to our Lambda, along with the status code, request ID, and the trace ID. And below the AWS Lambda, you can also see that there are logs attached to it. So you can see logs across the entire request across platforms. It's a super powerful tool in reasoning about what may be happening within your software platform. One of the biggest strengths for Datadog is the ability to do traces, logs, and metrics across all platforms. In this case, it's another trace, which is another piece of APM. It's a request that originally came in through a Ruby on Rails application. Right at the orange, it calls an API gateway, and that API gateway calls a Lambda. And there's actually another Lambda that is happening in the EU. By having a single place to think about software as services and software as systems that interconnect, Datadog gives you a way to jump up and down abstraction layers. We're using multiple platforms in a single request, and we're able to drop down into each one of the specific subdomains for each specific platform. It's a very powerful way to think about systems where you have these diverse platforms deployed. And then for logs, Datadog's Lambda layer automatically forwards CloudWatch logs to the forwarder, which then pushes them to Datadog. The forwarder can send logs and other telemetry to your account, such as Amazon S3 events and Amazon Kinesis data stream events. Deploying the forwarder via CloudFormation is recommended, as AWS will then automatically create the Lambda function with the appropriate role, add Datadog's Lambda layer, and create relevant tags like function name, region, and account ID, which you can then use in Datadog to search your logs. Because the forwarder is a Lambda function, it relies on triggers to execute. You can let Datadog automatically set these triggers up for you, or you can manually set them up to forward data as soon as they are added to S3 buckets or CloudWatch log groups. Once configured, Datadog's Lambda forwarder will begin sending logs from Lambda and any other AWS services you've configured to your Datadog account. Lambda functions generate a large volume of logs, making it difficult to pinpoint issues during an incident or simply to monitor the current state of your functions. And then you can use Datadog's log patterns to help you surface interesting trends to your logs. For example, if you notice a spike in Lambda errors on your dashboard, you can use log patterns to quickly search for the most common types of errors. We're also able to build up what is called a service map. A service map is going to give us a high-level overview over the overall architecture of our systems. In the top right, it says the past hour. We're able to change that time so we can see how our system architecture changes over time. So if we have independent teams that are deploying on their own and are spinning up their own services, this is a way to look and rationalize what is happening rather than going back to the architecture diagram that may or may not be a month or two out of date. Another thing to point out here is that some circles are red, some are green, and some are gray. Green means that all of the monitors associated with the services are passing. The red means that there is at least one monitor that is failing on that system. You can also see that there are icons for serverless functions, custom functions, etc. We can see the overall architecture, including databases and cache layers in our system. Going back to the levels of abstraction with APM and going back to that service level, this is the APM service page for a serverless function, and it looks just like the APM page for any other service application, regardless of the underlying platform. We can see on a service level how it's performing and how it's behaving. Critical points for how you monitor this thing that doesn't exist for 99% of the time is you want to pivot between abstraction layers. APM for service and application level problems so that you can dive into APM and see whether or not the service is giving back the intended responses. Is your latency too high, or is your JSON formatted correctly? Those service level questions you can answer with APM. You're going to use the serverless metrics and dashboards to see the state of your platform. How many requests are we getting? Where are they coming from? Are we taking longer in our Lambda services, and which ones are taking longer? And referring back to the service map for your overall architecture. One of the tricky things to do when you move to a microservices application is making sure that you're not running into circular dependencies, where you can't deploy an upgrade to one service without bringing down another. And having these kinds of unknown interdependencies that exist and that you're not aware of. Having the service map lets you think about these changes over time and lets you think about getting rid of a service, whether it may or may not be safe to get rid of it, so you can see if it's still used in production somewhere. The reason that we're building software is to deliver business value, and getting your metrics onto a dashboard so that you can quantify how your deployments are improving the overall business process is critically important in building your story for how and why you're building software. And the last thing that only really applies if you're doing serverless for a web application is adding real user monitoring to the front end so you can see the end user experience beyond getting the website to the end user, which is how are they interacting with it, etc. So now that we know how to handle our serverless environments, let's learn more about what we're using to build our Lambda function and how we're setting up our monitoring. Let's talk about all of the parts of our application before we get into the code. So we'll be using Serverless Framework for our function. It has a Node.js AWS template, so we can get started very quickly. It lets you develop infinitely scalable, pay-per-execution serverless applications. A single configuration file allows you to list your functions and define the endpoints that they're subscribed to. It provides structure, automation, and best practices out of the box, allowing you to focus on building sophisticated, event-driven serverless architectures comprised of functions and events. It has support for all major cloud providers, and the Serverless Framework CLI provides a single cross-provider developer experience. For AWS services, we'll be using Lambda functions, a S3 bucket to store our generative images in case we would like to use them later, and a Cloudflare cron trigger for executing our function. On the Datadog side, we'll be walking through how to set up the Datadog AWS integration, Datadog Lambda forwarder, and also integrating AWS X-Ray for distributed tracing through our function. For our actual function, we'll be creating it with Node.js. This is just a matter of my personal preference. You can choose whichever language is your favorite. We'll be using Canvas to create generative art that we are making based off of color palettes, which we get from the Color Lovers API. And after the images are created, we'll save them to an S3 bucket with the AWS SDK in case we want to get non-compressed versions of them later. And lastly, we'll use Twit, which is an API client for Node that allows us to interact with the Twitter API to upload media and construct a tweet. Lastly, I want to tell you a little bit about some background for Twitter bots. They used to be very popular a few years ago before Twitter made it so that you had to apply for a developer account in order to have access to their API. There are typically two kinds of bots. Some are generative image bots and the other are text-based, either tweeting out random words mashed together or Markov chaining data from various corpora. It was a great way for people who may not be exceedingly technical to get their hands on some code and try things out, and people made a lot of tools that made it even easier for people to accomplish the art that they wanted to. I'm going to tell you about a little bit about my favorite bots and resources if this is something that you would like to explore more on your own. First up is Soft Landscapes. It's an image bot made by V21 on Twitter. It uses something called Tracery, which is a tool to generate language and text, but bot developers realized they could use its structure to replace elements in SVG, which enabled a lot of flexibility with creating generative images. It's just a really pretty and nice bot, and it tweets out these images 4 times a day. The second bot I want to tell you about is Bracket Meme Bot, which is made by Darius Kazemi, who is a super prolific Twitter bot maker, and he thankfully documents mostly everything he makes. Bracket Meme Bot takes random categories of items from Wikipedia that meet a certain set of guidelines, like it must have a plural noun in its title and it must have at least 16 pages. And once it finds those categories that meet the requirements, it picks 16 of them at random and draws them onto a bracket like this. It's really silly, and you end up with brackets like SpongeBob SquarePants video games and underground laboratories. And I picked this one from Darius because he also keeps a GitHub repository of a lot of corpora that has a ton of bot makers pull from, which I'll link you to in the next slide in case you would like to try building some bots yourself. If you're interested in learning more about the tools started to make those bots, as well as other information on bot making in general, these links are a great place to start. Now it's time to code our bot. First thing we're going to do is navigate to the folder we want to use for our code and run serverless create --template aws-node.js. This is going to have the serverless framework set up a node template that's already compatible with what AWS is looking for. We've got 2 files that are important, the handler.js, which is where we write our bot code, and the serverless.yaml file, which is defining our provider, production environment, and other variables. We've got to change the service name in serverless.yaml to something that is relevant to our application. And then we also have to change the name of the function and the handler, if you'd like. However, if you change the function's name in serverless.yaml, you will need to make sure that it reflects the name in module.exports as well. Now we can run SLS deploy, which is short for serverless deploy, and this will take all of our files, zip it up, and deploy it to AWS. Next, you're going to log into your AWS console and navigate to the Lambda dashboard and click on that service that is the name that you chose in the previous step so we can make sure that everything is connected correctly. Since we can see that everything is hooked up, now we can focus on coding our bot. I'm not going to explain the code for my bot line for line, but instead just tell you how it functions. If you're curious, you can grab the code from github.com/RachelNicole/colorglimpse. And the way that this bot works is we're grabbing a color palette from colorlovers.com's API and saving it as an array. And once we have that array, we're creating some random generative lines based off of the color palette, and then creating a PNG of that image. Then we save the PNG to S3 and construct a tweet including the name of the palette and author that we also got from the Color Lovers API. Then we send it all up to Twitter so that it tweets the message and the art. And this is what it looks like. Then we need to set up a trigger for when the bot runs. Clicking on Add Trigger from your main Lambda function page will take us to the configuration page. You can choose CloudWatch Events, and it will walk you through the process of setting up a rule. We created one called Tweeting, which will run our function every 12 hours. You can set this up to run as frequently or as infrequently as you want. And that's it for the functionality. Now all you have to do is the instrumentation. We already described the process earlier about how with one click you can set up your AWS instrumentation, so I will assume that you've already done that. Out of the box, you'll be getting some logs already, and we just need to add a little bit more to our code. The first thing that we'll need to do is add some more information to our serverless.yaml file. Our serverless plugin has configuration options that you can use as needed for your specific use cases. You'll need to add your Datadog API key here. In addition to the serverless plugin, we're going to add AWS X-Ray, which lets developers trace distributed applications built using AWS products. For that, we need to head back to our handler.js file. You can run npm install aws-xray-sdk and require it in your Lambda function first, because you want to catch everything that happens after it's included. We add the code for capturing all HTTP and HTTPS traces, as well as capturing chained promises, which is super important because so much of Node.js is promise-based. You're going to run SLS deploy one last time so our instrumentation is fully reflected in our serverless function, and that's all we have to do for this specific use case. Now we're fully instrumented and we can take a look at our dashboards. Keep in mind that this example would be a singular function that would typically exist in a much larger ecosystem. We can see our traces, where we can dig into each individual request and see a flame graph of all of our API calls, as well as the tags, metrics, and logs for each specific request. Now, like I said, this is obviously a very small example, but I'm still able to get all of this information from using our AWS integration and a few lines of code. I can now go in and, if this was a larger system, be able to pinpoint problem areas and be able to close the product feedback loop with teams when I see areas of improvement. Thank you.